Okay, so this one, I have to finish this video without a microphone. Hopefully the sound won't be too terrible. Okay, so we're going through and computing all these terms in the Lie bracket. So we've dealt with the first one, and we're finishing the second one. So V1, W2, df, dy, dx. I'm just doing my, on the bottom, I'm doing the second derivative second. You can make your choices about what convention you want to use. Then I get V2, dw1, dy, times df dx plus v2 w1 d squared f dx dy plus v2 dw2 dy df dy plus v2 w2 d squared f dy squared. Now doing everything again, but with the w's and the v's switched. So w1 dv1 dx df dx minus w1 v1 d squared f dx squared minus w1 dv2 dx df dy minus w1 v2 d squared f dx dy dx, and then minus w2 dv1 dy df dx minus w2 v1 d squared f dx dy minus, this should not be a w, this should be a v here, minus w2 dv2 dy df dy minus w2 v2 d squared f dy squared. Okay, so now we get to go through and cancel things out. So I didn't see any terms in this box which had second derivatives of, there shouldn't be any second derivatives of f, right? Because I'm only taking, I'm getting a vector field. So when I apply it to a function, I should not see any second derivatives. And luckily, all of those go away. So here I have a d squared f dx squared, and it should get canceled out. D squared f dx dy will get canceled out by a d squared f dy dx. Luckily, mixed partials of coordinate in coordinate directions do commute. D squared f dy squareds get canceled out, and then finally df. Oh, I forgot to put this square in here, but d squared f dy dx will cancel with this one because the coefficients cancel. And if you go back and match everything up, you'll see that I have, okay, so I should have a v1 dw1 dx in front of the dx right here. I should have a v2 dw1 dy multiplying by a df dx right here. I should have a v1 dw2 dx in front of the d by dy, and here it is. I should have a, let's do this one, v2 dw2 dy times d by df dy, and here it is. And similarly, you can go through and match all of the w terms to here. So what we've done is we've shown that the Lie bracket is given in coordinates by this formula, which tells us that this coordinate-free formula for the derivative of a one form, the exterior derivative, is true because we managed to compute the difference between this and this, showed it was some function, some vector field being eaten by alpha, and then we figured out what that vector, based on what that vector field had to be in coordinates. When applied to alpha, we figured out what that vector field had to be, and then defining it in an invariant way, we showed that it's actually the same thing as the coordinate version. So the final thing to do is to show what happens when I'm considering a one-form in general. So in general, and higher forms. So in general, this same formula holds. So I'll just rewrite it. So this formula holds more generally. So in your book, Fortney goes through the work to show that for any one form on Rn, for any n, d alpha applied to the pair VW is equal to V applied to alpha at W minus W applied to alpha at V minus alpha applied to the Lie bracket of V and W. And then when I'm trying to compute the global formula, you have to be careful with the signs to make sure you know how you're plugging in your Lie brackets correctly, but what you end up getting is a generalization of the formula we had last time. So d alpha applied to V0 through Vk is the sum from I equals 0 to k, negative 1 to the I, Vi at alpha of V0, so plug in everything except Vi. And then I want to also add the sum from sum over all I less than j of negative 1 to the I plus j, and then you have to cleverly make sure you're sort of plugging everything in correctly, but you end up getting all the Lie brackets showing up as this sort of term that you have to subtract off or add off, as the case may be, in order to make sure you have the right formula. So this is, so the first formula is for alpha a 1 form, and then this is for alpha any k form on Rn.